Hi. In this presentation introduces a new neuron model that could help to improve our understanding of perceptron and to clarify key components like the activation functions used in AI learning algorithms. In this neuron model, each neuron works as a small lookup table, where binary inputs correspond to a binary output, so the only values it handles is 0 or 1. In this case, we are going to use two kinds of neurons, one with one input and other with two inputs. For inputs 0, 0, the output is P0. For inputs 0, 1, the output is P1, etc. Each input corresponds an output value P, as shown in the figure. Let's suppose we connect the neurons as a tree with the p-values as displayed. We are going to train the neurons with a given input and tell them if the output is correct or incorrect. This is known as supervised learning. Each input selects a path in the network, and each cell has a counter for each path. In this case the output is correct, then we decrease the cell's counter in the path created. Now, in the case of an incorrect output, the path counter increases. When it reaches a threshold, the cell output changes for that path. In this way, the neurons can learn to output the correct value. Biological neurons can connect randomly. We will model this behavior, ignoring possible loops with our binary neurons. As discussed in the previous section, the neurons seem to approximate our desired value, depending on their inputs xi. In our simplified model, we have reduced the entry cells to a single input cell. The single input cell transforms the inputs before they enter a function. Based on the simple idea that similar inputs generate similar outputs, we can use algebra to sum all the transformed inputs and create two categories, where the sum indicates the degree of similarity among the inputs. If the average is greater than 0.5, the output is 1. Otherwise, it is 0. If we apply the MNIST dataset as input, a significant issue arises with the background pixels. Since a large portion of the image consists of background pixels that are consistently black across the dataset, the model only learns the value P0 for these pixels. As a result, if a cell input has a value of 1, it will return its untrained value P1, leading to distortions in the summation that, if accumulate, can negatively affect the classification results. Therefore, it is necessary to apply noise to the inputs so the model can learn P1 during training. To achieve this, we will convert the binary neuron to a binary probability model. Next, we move to a probabilistic model, which involved adding noise to the neuron inputs, transforming binary outputs into probabilities. As shown, a 10% noise level in the data is enough to clearly recognize the numbers in the images. As a result, we use a 10% noise level, and the grayscale values in the image correspond to intermediate probabilities within the 0.1 to 0.9 range. Therefore, the neuron will output a 1 with the following probability. Using the output probability of each neuron, create for groups and approximate the output of each group to Z, where Z is the average output probability of all neurons. Consequently, the probability of 1 for each case is shown in the table. The final result is Z squared times the expression 3 minus 2Z. And this equation resembles the logistic function. Here it shows the comparison with the logistic function. For simplicity, the logistic function will be used. This is the neural tree model. However, as we discussed in the previous section, the sigmoid function receives the average output of the cells. We can break down the equation into the following equations. As the defined tree closely resembles the sigmoid neuron, which is well studied and widely used, we employed a commonly used architecture, fully connected trees arranged in layers. Each layer consists in an input vector X creating an output vector Y. Every element in vector Y has a tree with its own weights and bias. Here a brief summary of backpropagation algorithm. We start with the initial transfer gradient using the error function of the current output and the desired output. Then we calculate the transfer gradient to pass it to the previous layer. It's a relation between the error function and the inputs X. Finally, we update the parameters following the gradient descent equations. And the process is repeated in each layer. At this point we only discussed a sigmoid function that has a probability range of 0 to 1. Besides the data distribution, the weights modify the alpha and beta, that corresponds to the slope and offset of the function. In the case of the MNIST dataset, if we have a neural tree that learns a feature, such as the number 2, adding noise reduces the probability of detecting this feature. However, if we continue adding noise, the feature appears again, but inverted. To take advantage of this and process the same feature within the same neural tree, we could use two sigmoid functions in the same tree. The resulting shape closely resembles an inverted Gaussian bell curve. For simplicity, we directly use a Gaussian bell curve, as, in practice, with multiple perceptrons, it produces results very similar to those of the inverted Gaussian. Using this Gaussian bell curve enables the learning of two features within the same neural tree, particularly in the context of image data. However, if this is not necessary, the network can adjust the data distribution to approximate a sigmoid-like function by learning the parameters alpha, omega, and beta. But what if we add 3, 4, or n logistic functions? In that case, we obtain a cosine wave. In practice, the cosine wave would only learn alpha at very low frequencies due to the condition that similar inputs should create similar outputs. From the graphs, the sigmoid function approximates half of a wave, the Gaussian function approximates a full wave, and the cosine wave appears to be the most general function, encompassing both by learning the frequency alpha. Experimenting with different activations functions based in Gauss and cosine, we have the following, in probability range of 0 to 1. Here are the activation functions mapping the probability from -1 to 1. More details can be found in the following links. Thank you.